Hello, today we will be discussing how pollen production and global warming impact air quality and allergies.
For this study, our research hypothesis is that as global warming continues to escalate, the concentration of pollen in the air will increase and proportionally decrease the quality of air, leading to more frequent or worse symptoms of respiratory issues such as asthma or allergies.
Individuals with asthma and allergies should be notified if these allergy seasons are intensifying and becoming longer because of climate change, because it can affect their daily lives. So gathering accurate information on the measurements of pollen is important for understanding health impacts, not only to people sensitive to pollen, but also people with respiratory issues. Improving pollen collection and monitoring can better inform the public so they can make informed decisions to manage their allergies and improve their quality of life. Eighty-one million Americans experience seasonal allergies, so a large portion of people are affected by pollen and spend over $3 billion on medical costs. Ha Almost half of these costs are from prescription medicine alone. Burning fossil fuels releases carbon dioxide and other pollutants that can agitate the respiratory system and cause people to be more susceptible to pollen allergy symptoms. People who live in communities with higher levels of vehicle traffic and industrial pollution face increased risks of pollen symptoms. Only 85 pollen stations were operating in the US in 2018.
So our research approach for this study will be to have 25 site collection areas across the United States to capture different climate levels across the country. It will be a year-long study with data collected daily. The daily data collected will be the daily resolution of pollen and PM measurements, as well as the atmospheric conditions, such as the temperature, rainfall, wind speeds, etc. The atmospheric instruments that will be used will be an anemometer to get wind data, a rain gauge to get rainfall, and then a basic thermometer to get the temperature. The pollen and PM measurements will be gathered using the Burkhardt spore traps, WIBS, Swinson Polino Jupiter, and the ABS 300, which will go into further discussion on the future slides. To get the health data for our allergy specific analysis of this study, we will um, we will get data from healthcare professionals in the specific testing site regions.
The Burkhardt spore traps is a commonly used instrument to collect pollen concentrations in the air through a volumetric slit type air monitoring device. How it works is it extracts air at roughly 10 liters per minute through a 14 by 2 millimeter slit. The air is then deposited onto this adhesive coated tape that is attached to a rotating drum that spins at a steady state. Due to the steady state, the amount of pollen concentration can be divided into strips during each hour of the day to then be put onto a microscope slide and stained and covered with a cover slip to be placed under a compound microscope using 400 times magnification to identify the spores and be counted by a certified professional. This instrument relates pollen concentrations in the air with human respiratory volume. It could be used in aerobiological monitoring to evaluate allergen exposure for public use.
The wideband integrated bioaerosol sensor, also known as WIBS, is an instrument from Droplet Measurement Technologies that detects and characterizes airborne biological particles such as pollen using UV-induced fluorescence and light scattering. It provides real-time particle counts and categorizes them based on their fluorescent signatures. The latest model is the WIBS 5, which can identify trends and patterns in the bioaerosol behavior at finer scales than any filter-based method. How it works is the particle will pass through a UV laser, and elastic light scattering will be measured to determine its size, shape, and biological concentration. The fluorescent emissions will be captured by detectors that identify wavelength bands related to its biological origin. No filters or slides are required for this method, yet it does entail extensive calibration. More about the WIBs is the particles pass through the UV light, producing wavelengths, such as a range of like 285 nanometers or 375 nanometers. The UV light then excites different intrinsic biological fluorophores, such as tryptophan, NADH, or riboflavin, within the particle, which is then used to identify what it is. The fluorescent emissions are also captured using PMTs, and the light scattering is recorded. That is what is used to estimate the size and other properties of the particle. And then fluorescent ratios and fluorescent fractions are produced to place the particle into its fluorescent biological aerosol particles or its non-biological particles. And then it can even go and divide it into more specific subgroups. Next is the Switzer Pollen Jupiter. This is a bioaerosol monitor that detects and classifies airborne particles while also producing holographic images for a more detailed analysis. So how this works is the ambient air is drawn into the instrument, and the particles, which range from about size of 0.5 to 300, pass through the optical chamber with multiple different detectors within it. Three-dimensional holographic images of the particles are then generated, which causes the biological particles to become fluorescent. The UV light causes the biological particles to become fluorescent and measured based on their brightness and time of illumination. This produces high quality and reliable data, which is really suitable for field use. It utilizes the measured airflow Q to calculate the concentration using the equation C equals N over QT. So this also is able to compute relative fluorescence spectra by dividing each of the detector's measured fluorescent identity or intensity by the sum of all the detector intensities. This provides accurate measurement of the particle concentration and its type.
A more recent advancement in pollen detection is the ABS pollen sense. It uses AI sensors and images to determine the amount of airborne pollen in a given region. Like the prior detector, it uses ambient air with a constant flow airflow system. It can collect images of particles that are less than 5 micrometers, and it uses AI to reform the image and collect data on the pollen particles and produces a pollen count and a daily pollen concentration of pollen granules. And it can categorize pollen by its taxon. It is consistent and it provides real-time pollen concentrations with only a 1-minute delay. This is strongly correlated with other gold standard measurements, as mentioned before, and manual counting methods. This hardware is also mobile and can provide pollen monitoring at the local level. The physical counting systems or ways of collecting data will be cross-referenced with automated instruments to ensure the validity of the systems used. The average concentration of pollen will be recorded on an hourly, daily, weekly, and seasonal time scale for each instrument. This can be used to find the range, average, medians, and maximum values, which will outline pollen trends based on timescales. This can also be used to determine seasonal trends and help track patterns of pollen levels to determine when pollen concentrations will be at their highest. By collecting pollen in 25 different locations, environmental effects on pollen can be observed, like which pollen types are most prominent during certain times and when these pollen concentrations surpass a threshold. This is essential in determining how pollen affects the health of populations. Our hypothesis is twofold. One is that global warming will escalate the concentration of pollen. This has been seen in recent studies. Pollen season is starting 20 days earlier than it did in the 1990s. There's also a 21% increase in pollen concentrations during pollen season. Warmer weather and more carbon dioxide leads to more pollen production per flower, and other effects of climate change, like pressure changes and humidity changes, can break down pollen spores to smaller particles, which can then enter the lungs more easily. Another impact of this hypothesis is that respiratory issues will increase with increasing pollen concentrations. Hay fever specifically can have serious impacts on children, causing rashes, hives, difficulty breathing, and even an upset stomach, which impacts productivity and school performance. Allergies can also trigger other health issues in children, like shortness of breath, chest tightening for people with asthma. And allergen exposure can make you more vulnerable to viruses by inflaming the respiratory system.
So what does this mean for our stakeholders? Our stakeholders are mostly people with seasonal allergies or experiencing asthma, and the air quality monitoring devices that agencies and healthcare professionals use. But how does this affect them? It can influence how they make informed decisions surrounding air quality. So this could include where they're living, and it can impact their quality of life / daily comfort, since asthma and seasonal allergies have nasty side effects, and it can improve respiratory health if less patients have to go in, if more people stay indoors. And another impact is indoor air management for good air quality.
Here are just a list of our references used for this presentation. I hope that you guys learned something a little bit about air quality and how it impacts allergies. Thank you.